Okay, here is the first lesson from chapter 1, and it's going to seem easy, but it's very conceptual, and so please pay attention and make sure you understand all these very important concepts that we're going to build on in this course. So what is a function? I love this function machine and this idea that we can take a number like 2 and it goes through this machine and out pops like a 4. And so we would show that on our table with a 2 going in and a 4 going out. And let's say we take a 3 and we put that in and it goes through the function machine and out comes a 6, et cetera, et cetera. Let's put one more in. Let's say we put a 4. What do you think is going to come out of this machine? That's right. An 8 is going to come out. And so this idea of a function, we need to make sure we understand what that involves. And so the first thing we're going to talk about is what the X column stands for. X aligns with the input, like what we're putting into a function. It's also our independent variable because we can pick anything to put into our function. What we pick is independent. And the domain means the numbers that we use for our X column or our input. That's a domain. And so it's also very important to know what the Y column stands for. Y is the output. When you put a number into a function, well, out comes a number for Y, and that's our output. It's dependent. The reason why it's a dependent variable is what we get for Y depends on what we put in for X, and that's why it's called dependent. Also, this set of numbers that end up in the domain, end up in the range are called the range. So in the Y column, those are the range. This is important. Sometimes people are like, why do we have to memorize? And I get it, except for memorization actually allows us to live in some very common sense ways, right? And it's going to allow us to build on our understanding of math as we proceed. And so please memorize what goes with X and what goes with Y. So we also want to talk about a function using something called, well, a vending machine. So when I'm looking at this vending machine and I push an A1, out comes, oh gosh, surprise, a Snickers. I didn't know what's going to be behind there. And I push another A1 and, we expect, hey, you push A1, Snickers come out. So far this vending machine is functioning. Let's say, well, who knows what's going to happen when we push the A2. Oh, are those Skittles or M&Ms? I can't tell, but good. And so when I push an A2 again, I would expect what? The same thing to come out. I'm like, yes, this vending machine is functioning. So when I push A3, I see, looks like a bag of Twizzlers. So when I push A3 again, I should get a bag of Twizzlers, but you know what's going to happen. That's right. No, I'm going to get carrots instead. And so what I would say about this vending machine is it's not functioning. And the reason why I'm showing you that is it's very similar to this table. And why that is because with this table, you put in a 4 or you push a 4, thinking about a vending machine, and out comes a 9. And the second time you push a 4, out comes a 13. This is not a function. It's just not functioning. And so eventually I'm going to tell you it's not a function, and it's not functioning. Eventually we'll get to the definition of a function, but I think it helps to think about vending machines. And so also, thinking about vending machine, wonder if you've got this vending machine, you pick A1 and out pops a water bottle. Okay, A1 should also pop out. Good. Okay, what's behind A2? A2, water bottle. Okay, A2 should also be, yep. A3, water bottle. A3, water bottle. So it's functioning, isn't it? I mean, this vending machine only makes water bottles, but it's still functioning. And that's very similar to this table. No matter what you push, whether it's a 0, 1, 2, 3, 4, 5, out comes a 9. No matter what our input is, our output is still a 9. And that is a function. Okay, this is a function. And so what exactly is a function? Hopefully I tell you on the next slide. Okay, for every x, there can only be one value of y. So when we look at these two tables, we're like, wait a minute. So one of these tables is a function, and one of these is not. And what's the difference? In this one, our x values are all the same, and this one, our y values are all the same. Which one is allowed? So let's think back to our vending machine. This would be a vending machine where if I push 5, out comes a 1. Well, the next button that I push a 5 for, because sometimes, right, in vending machines, like especially if it's a popular thing, like Three Musketeers, I don't know what's popular. Well, not in our school, right? Nothing with that much sugar is going to be in our vending machine. But if you push a 5 and out comes a 1, you would expect every single time you pushed a 5 for a 1 to come out. Not for table 2, that just didn't happen. Now, for table 1, that just didn't happen. Now for table 2, this is like a water bottle vending machine. You push 1, out comes a 2, push a 2, out comes a 2. You know what? It's okay for this to happen. This table just makes 2. And if you're a visual person and like to think about graphs, let's look at a graph. What would this graph look like? Well, it would be, x would always be 5, right? Because each of these, like 5, 1, represents a coordinate point 5, 1. That would be 5, up 1, 5, up 2, so over 5, up 2, over 5, up 3. No wonder it's not a function. This is x equals 5, and we know vertical lines are not functions. We will come back to that in just a few more slides. Same thing with this. If we were to graph this, 1, 2 would be over 1, up 2, over 2, up 2, over 3, up 2. This is going to be a horizontal line, y equals 2, which is a function. Once again, we'll review that in just a little bit. I'm getting ahead of myself. Sometimes we can look at what's called a mapping, and that can either represent a set of numbers that's a function or not. In this case, it is a function, right? For every x, there's one y. When 1 is, we push 1, we get out a 3, et cetera, et cetera. You can see clearly. Let's look at this one. This one is not a function. When your input is 2 the first time, your output's 8. When your input is 2 the second time, your output's 2. That's not functioning. When x is 2, it can only align with one value of y. Pick a number, 2. Either align with 8 or align with 2. All right, so not a function. Not. Okay, so let's see what we've got on this next one. So sometimes you're going to see a set of coordinate points. So instead of a table, you're going to see a coordinate point. You just want to check, hey, for every x, does it only match up with one y? And in this instance, what we've got, x is 1, x is 2, x is 3, x is 4. This is a function. We don't have any repeating x's that match up with a different y. Okay, so when we look at graphs, once again, this is just a review of Algebra 1, but we build on it in important ways in pre-calc. So function or not, we have the vertical line test. So here's our vertical line. And basically, if you had me for algebra, you know that the vertical line beeped anytime it came across a point. So beep, 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 beep. Okay, note. When the vertical line is hitting this graph, which is just a set of data points, the line never hit more than one point at a time. So this is considered a function. So if we looked at a different set of data points and we did the vertical line test, we're going to go beeping once, but then here, beep, beep, and we're in trouble, right? Beep, beep. Okay, this is not a function. If we stop right here and look at why it's beeping twice and why that means that it's not a function, we come to the same understanding as what we did a few times before. We look at when x is 1, right? If we want to put this in the table, when x is 1, the first point says y is 2. Well, when x is 1, gosh darn it, y is also 5. We can tell from this table, from our understanding of tables, this is not a function. So we could either take our graph and turn it into a table, or just use the vertical line test to show the same thing. This is not a function. All right, so look at this. What is this? This is a quadratic. Of course, it's a function. If we did the vertical line test, we would see that for every x, there's only one y. Quadratics are functions. Function or not, what kind of function is this? This is exponential, so of course, I just asked you what kind of function is it. We know exponential graphs are functions, even though this is a little bit of a weird graph. It comes from a graphing calculator. All right, now you may think, oh, yeah, Miss Overby, this is a quadratic, so it's a function. No, it's not a quadratic. A quadratic, the graph, a parabola has to be right side up u or an upside down u. This is actually a conic section. It's like a quadratic conic section, but it's not a function. And so when we do conics down the road, you'll understand how conic quadratics are different than regular quadratic functions. But here, obviously, no, for every x, there's actually, except for at the vertex, for every x, there's actually two y's, which makes it not a function. Okay, so once again, let's look at not only linear graphs, but let's look at linear equations, because we're going to be asked if equations are functions or not. And so just get used to seeing what linear equations look like. Once again, I realize we're doing Algebra 1, so bear with me. Just make sure you understand this inside and out. Linears are functions, quadratics are functions. Give yourself time to look at the graphs of quadratics and the equations of quadratics. I put these last two in because sometimes people might want to fool you, right? They might want to say, ooh, is that a quadratic? Is that a function? Sure. If we rearrange that, it would look like, just bring that 3x squared on the other side. So you'd have 3x squared plus 2x plus or minus 7. Don't be fooled by that. All quadratics are functions. Absolute values, remember, those are the V-looking graphs, whether they're right side up or upside down, and this is what absolute value equations look like. So get used to that, and yes, absolutely, absolute values are functions. And our last thing are exponentials. Exponentials are functions. Get used to what the graphs look like and what the equations look like. So those were the four functions we worked with in Algebra 1 and Algebra 2, right? Those were our big ones: linear, quadratic, absolute value, and exponential. All of them are functions. So let's look at equations and decide whether they represent a function or not. And so I'm looking at this. Obviously, y equals 3x is a function. It's linear. But I want to remind you that when you see x in the denominator, that is not linear. In fact, put that into Desmos and graph it, or put it into your graphing calculator, and you'll see it's definitely not linear, and it's not a function. All right, so when we're looking at y equals x squared plus 3 and x equals y squared plus 3. Hold on one second. I'm going to pause for a second. Okay, I had to pause because even as I was saying it, I was like, no, you're not right. So I want to come back. This is not linear. It is a function. It's just going to look something like this, where we're going to have an asymptote right here when x is equal to 0, because obviously x can't be equal to 0. So my bad. Please go back and say this actually is a function. If we went ahead and did our vertical line test, yes, it is a function, but no, it's not linear. So, whew, all right, as soon as it came out of my mouth, I was like, that is not right. All right, so let's go ahead and focus, though, on this. This one's a really important one. Y equals x squared plus 3 is obviously what? It's a quadratic. It's lifted up 3. It's going to look like this if we look at it as a graph. But x equals y squared plus 3, that's not quadratic. And if we try to isolate the y, we could see y. So let's go ahead, and I know we don't like the variable being on the right side, at least most of us do, but let's go ahead and kick that 3 over, and let's isolate y. When we do that, when we take the square root of both sides, we have to put the plus or minus in front of x minus 3. So right there just tells us, hey, anytime we want to find y, we're going to get two answers, plus or minus. So for instance, if we were going to do a table and we were going to plug in, let's pick something good. Let's pick 7. Let's say x is 7. Well, when x is 7, we plug 7 in. 7 minus 3 is 4. Square root of 4 is 2. Uh-oh, that plus or minus 2. So when x is 7, y can be either equal to 2 or negative 2. And we can instantly see that is not a function. Now, if you don't want to work that hard, you can just decide that you're going to trust me, and you're going to remember that when you see equations with y squared in them, they are not a function. And you can trust me, even though I did make a mistake up here. I usually catch my mistakes, and that's what's great about humans. We do make mistakes, and if we can catch our mistakes and learn from them, even better. So when you see a y squared in an equation, that's your sign usually that it is not a function. All right, one last one, and that is looking at y equals 5, x equals 5. And we talked about the difference between those two. Y equals 5 looks like this. and oops, 1, 2, 3, 4, 5, yep, and x equals 5 looks like this, 1, 2, 3, 4, 5. Obviously, x equals 5 is not a function because when x equals 5, 5 matches up with anything, right? Any of the y's. X is 5, y is 0, x is 5, y is 12, negative 5, negative 7. So that's not a function. Okay, so that was a review from Algebra 1. Now we're moving into a review of Algebra 2. And I want to say very few pre-calc students come in to this class remembering really how to find the domain and range of a graph. And so I want to give you something that I think will really help you. First, we're going to focus on finding a domain. And we've got to remember that domain refers to the x values, right? Domain matches up with x. So we're going to look to the x-axis for our answers for our domain. And so one thing that helps is using vertical lines. So what I'm going to do is use this vertical line. Oh, hopefully not move my graph. All right, use this vertical line and say, how far, if I start at the origin, how far to the left can I go before I stop seeing my graph? So like I couldn't go to -3 because my graph's not there, right? So I'm going to pull back in and I'm like, oh, my graph starts at -2 when x is equal to -2. So for my domain, it starts at -2, and where does it end? It ends when x is equal to 3. So I want you to remember when you're asked to find the domain of a graph, you're looking at the x-axis for your answers. All right, now, how do we write our answers? This is something new for pre-calc. I'm not sure how much they did it in Algebra 2 Trig. We're going to write interval notation in interval notation form. And so that has some rules. First of all, if we're going to include the number, we need to use a bracket. So is -2 part of our domain? Absolutely. There's that point right there at -2. So to write our domain, we're going to say our domain, we could use the 2 dots or we could use equal. We're going to include -2. Now for interval notation, we always start with the leftmost number that we see on our graph. The lowest, the least number goes first. And then we put a comma and we tell the reader where our domain ends, and this time it ends at 3. Are we including 3 in our domain? Absolutely. Now the cool thing about interval notation, which is true about the cool thing about math, is that no matter what language you speak, you could look at this right here and understand, looking at the brackets and the -2, 3, you could understand what that meant without any words, which is pretty cool. All right, so to find the range, we're going to go ahead and use a horizontal stick. So the range is basically, the domain was like how wide, how far, do we go from the left and the right. And the range is concerned with height, how tall and how low. So just like with the domain, we're going to see how low can we go and still see the graph. For right now, just real quickly, I'm going to move the domain lines because they're kind of interfering with us seeing. I can't go down to -2. There's no graph there, So I have to go move up and I see, oh, the lowest point of my graph is at -1. And the highest point of my graph, the tallest point of my graph, is at 1. Now we see there's a point at 1 when y is equal to 1, and there's a point at y equals -1. So our range is going to be, we're going to start at -1, always put our lowest number first and include it, and our highest number is 1. We're also going to include it. So that's our range. Some people like just going ahead and drawing a rectangle around the graph, and then they remember, look at where your rectangle intersects the x-axis, and those numbers are your domain, and see where your rectangle intersects the y-axis, and those numbers are your range. I think this is the best way to find domain and range given a graph. So let's try it again. So here we go. We're going to go through this a little bit faster. When we're looking at domain and range, we're looking for the left side, but we see this arrow. Okay, and this arrow means, see how the graph is going? It's not going to the left far, really fast, but it is going to keep going. So we're going to have to keep moving our left bar over, aren't we? And we could spend the rest of our lives moving our left bar over, but we have better things to do. We realize, oh, this domain, actually, the furthest over it can go, we can't keep up with it. So we have to use the concept, the idea of infinity, to describe that the domain starts actually at -infinity. Now, -infinity is not a value. I want to make that clear. It's a concept. And so with negative infinity, we can't use a bracket because it's not a value. It's not a point's not there. It just reflects that there's really no starting point to the left of this graph. And then you know that the same thing is going to be true for the right side. There's no ending point either, because as this graph moves to the right, it's slowly going to keep. I know making that a little bit more than it really is, okay? But it really is going to keep moving to the right to where we're going to go all the way to infinity. So we would say our domain starts at negative infinity, which just means it really, we don't know where it starts because it's way, 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 way out there. And it ends way, 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 way out there. Well, actually, it never ends, right? That's what infinity means. All right, so that would be tough to draw a rectangle with that, right? But we see those arrows and we need to know what that means. All right, so the horizontal sticks we're going to use for range. And once again, we're like, oh, how about -5? Oh, no, those arrows are pushing me down, right? So our range is also going to start at negative infinity, okay, because the lowest part of the graph, it doesn't exist. I mean, it just keeps going and going and going. There's no number that we can use to represent it. But there is a number we can use to represent the height of the graph, right? The tallest that the graph can be is 4. And so that's where the highest number we can find for the range for the y values is. And we're going to use a bracket because we are including 4. Whew. Okay, let's do one more. All right, so we've got something different here. Do you guys see right here, and girls, do you all see right here that open circle? All right, let's talk about what that open circle means. When we do our domain, it's really easy to see that we're going to start, our farthest left point on the graph is -3, right? So we're going to move that. All right, so we're going to say our domain starts with, we're going to include -3, so that's a bracket. And it ends, so this gets a little tricky because we can see that the graph clearly ends at 3, but yet that's an open circle. Well, we're going to work more with graphs and understand those open circles better, but they're a placeholder. See, there's no value. When x is equal to 3, there's no value for y. But when x is equal to 2.99999999999, there is a value for y. So that open circle says, yeah, we're missing a value when x is equal to 3, but we have it all the way up till x is equal to 3. And so what we're going to do is we're going to say, well, our domain does stop at 3, clearly, but we can't use a bracket because 3 is not part of our domain, because when x is equal to 3, there's no y value. And the y value is actually the graph. The graph represents what our y values are. And so that's our domain. So then when we look at how tall are we, how short are we go to 2, and once again, it looks like, okay, I drew this graph, so it's not the best, but it should look more like, okay, the height doesn't quite reach 2, but maybe it does with the open circle. So we've got the same idea behind the range, that the range is, oops, and look at me, I'm starting with the highest point. So let's back up. The range has to start with how low is the graph, and the graph looks like -1. All right, really maybe a little closer to -0.9 or something, but let's move this red because let's just agree it's -1. So the range is going to start at -1, and then it's going to stop at 2. That's the highest point, but there's an open circle at 2, and so we're going to do that parenthesis. All right, you're going to get lots of practice with this, but this really sets down the rules and what's behind here. Use a parentheses if you're excluding the number. You always use parentheses when dealing with a whole. And we'll talk more about wholes later on in this chapter. And that's it. Yay, we made it. Once again, a lot of concepts. Seems easy. Please make sure you understand these. Thanks for joining me. Bye.